Graphic animation, again, lesson 20, part 1. I have to admit, I think this is more of a demo than it is a lesson, just so when I started, I created a directory called lesson 20, and yeah, we'll see when we get through. Okay, this is going to be long detailed, maybe more than what you want to hear, but as I started with at Glen Hewett's great demo, and this is what I ended up with. His just had a good background, star field, and a whole bunch of globes going round and round and round. I'd cut it short here, and ended up with mine was a Mickey Mouse with some baseballs going round and round and round and round all over the place. And I was going to this venture here will show you how I got here. This should stop pretty soon. Oops, there's what his looked like with the star field. And the stars, you couldn't see them when it's full screen, the stars are all moving all down and the globes going round and around. Mine has Mickey with the baseballs going round and round, back and forth across. Okay, here's Glen's. There's a link to it. It's on GitHub. It's been there for a long time. I type this in and get it. You got the source code and everything comes with it, and it's outstanding to just to watch. This here was for my own benefit. This here was just all the checkpoints as I went along. Major revisions. There was a lot more, but these were the major ones. And this is what they look like. First was a screenshot of Glen's, and then I got my own startup going, got my screen, and I copied his sphere for my Sprite and got that done. And I was ready to go. So I changed colors on the background and added some more sprites, and this is what I had. The globes didn't look so good on a light background. Needed a black background, so I changed, went over to baseballs, and put 5 of them on the screen for whatever reason. Then I come up with a batter for in the background and added some more baseballs. Now these baseballs didn't move. Well, they did. If I moved this one to the left, all of them went to the left. If I went up with it, they all stayed together. They just all moved according to wherever I coded it. And then I went in and cleaned up all the code at that point there, put some words in it. This was a 320 by 192 by 16 color her H screen 2. And I could use BASIC to print the words on the screen. So I got it all cleaned up at that point. Then at this point in time, nothing really was going on with the balls, but I knew what I wanted to go do from this point out. So I kind of started all over. I took the code and I just kind of started all over. I put a different background. I went to 256 by 225 by 16 colors. Different background, needless to say. Got Mickey, a white background with the character of Mickey, and I put 16 balls in a circle. And what when you looked at it, it looked like they was going round and round and round. All it was, there was 16 on there. I restored the screen. I turned this one off, turned this one off, turned it back off, turned this one, so on and so forth, where it looked like it was going around in circles. No fancy automation, just that was my next cut. And this was a big cut. I went to a coordinates table, row column, and added, I don't know, I was at this point using 5 balls. And this would kind of follow the path that Glen's did, round and around and over and across and up and down. So it was a major rewrite a lot of the code to get the well, not rewrite, just adding all the coordinates to it. And this is what I ended up with, okay? Added words, some ending stuff, keyboard stuff, and variable stuff, meaning you can, when you run the basic program, when you start up, it asks you how many baseballs you want. I think it ranges from 4 to 12. How far apart do you want them? Uh, how many loops do you want to do in watching this thing? And last but not least was one for optimization. One way is normal, which is normal putting the baseballs on the screen and taking them off. And the other way was stack blasting them. And look at towards the end of this here, we'll see the difference in that. This one here is not in there. So I thought this was kind of neat looking. When I was testing, I turned off the restore function, and I just let it run. And this is the path of the ball. Okay, come around this far outer edge, and you consider all the balls follow the same path behind one another to come down and around and keep getting smaller and smaller. And this is why I stopped it here. You can see there were 6 balls here. There's one there, one there, one there, one there, one there, one there. I just thought it was a neat looking thing on the screen when I was just turned the restore function off. Okay, stuff we've looked at many times. Your basic, if you're task 0, here you go. If you say task 1, you'll get using the second part of this MMU registers. Blocks 38, 30 through 33 is where your high-res screen is. And the only other piece is HR. That's if you do HBuff or HGet or HPut, it uses that there in the addresses. Okay, here's what I ended up with. Most of the time it runs in task 1, which is kind of standard. Other than this is where disk basic normally resides when you're in task 1, but I use it for my coordinate table because the table is quite large. And I use the same block 35, but I put the work area and the letters function that I had in lesson 18 in there. All right, when you flip back to task 0, yeah, I changed it from, because these blocks over here would be 38, 39, 3A, 3B, 3C, and so on. I switched to have 20, 21, 22, 23. You notice a similarity in that. So what I did here, okay, we note when that background Mickey is a compressed image, it's loaded by basic into blocks 0 and 1, and I pull it out of there. To start with, it unblocks that image and puts it in blocks 30 through 33. So there's my image now in a startup. The next thing it does is it copies that image over to blocks 20, 21, 22, 23. I don't know if you know where I'm going or not, but that way I got a restore function. I can change anything on the screen and I can restore it right from here without saving it, because the Sprite itself is 91, baseball really is 91 bytes. So I said, okay, well, I'll just be able to restore from here back here. So let's assume we got one of them sprites or baseballs right here at 6,000, right in the middle of Mickey. Okay, when it comes around going through its cycle of moving all the balls, it has to refresh the screen and before it puts the new one on. So I put load up wherever the 6,000 on register X, I believe, and then I go to task 0. So I'm still working down out here. System is still down here where my program is, but this is what I'm looking at. So I can take the 6,000. That would have taken that image out of there are all the different 91 bytes. It's say 7 columns and I don't know 13 rows. Anyway, and then I just put it down here. I go through all 91 bytes. Load, store, load, store, load, store. I got them in there. I say task 1. I do a load, store, and it's copied. It was restored back to what it originally was. All right. When I was looking at that, when I was going, I said, one time I said, that's an awful lot of moving around. Let's not do that. This temporary save area was down here. So I said, I don't need that. So I come over here again. Let's do the same thing. If it's at 6,000, I put that in register. I go to task 1. I load up register with what I'm going to repair, and just say, I'll go to task 0, load it up, say task 0, store it. Go back, load up, store it, back, forth. I have to do that 91, say 91 times. It's half of that because I'm using 2 bytes at a time as opposed to load, store, and then, so anyway, it was made it a lot quicker doing the restores. Okay, here's that lower part of memory from 0 to hex 2000. A program is loaded in here at E00 where we load most of this stuff in here. And down here is if you're in a low resolution, which you turn your machine on, it's down here at hex 400 to 600. At the end of this load, then I got 2 programs inside that source code. This one args at E00, this one args at 400. Well, in fact, there's 2 pieces. One of them args at 400, one of them args at 500. And that's the image display, like we talked about, unpacking that image of Mickey. This program gets everything set up. It's all the stuff it needs to have set up to start the program. All the registers, blocks correct. And then it does a jump subroutine down to 400. 400 unblocks that display and puts it in the blocks 31 to 33. Does return sub. It does some stuff, and then it actually puts it up on the screen, and it comes back, does a jump subroutine to 500, which is the copy part. Then it copies it from 30 to 33 to 20 to 23, like I showed in that other slide. So let's just show you how I do it. So this code down here is never used again. So it saved a lot of code not appear that I could use for other stuff. And just this code is, in a sense, throw away once it's used. Okay, part 2. I was going to cut this in half, but it's not that long, so let's get through here. Part 2, overview of the steps to get here. Lots of detail, probably too much, and the optimization. Okay, we've done seen this here before, but you can see both of them running. Okay, one of them's running a lot faster. This one here is just normal. His was stack blast, and this was just normal, putting stuff on the screen. And I will show you, I will change this one here later on so you can see how it actually worked. If I can get off of this screen here. Again, this was my steps, and the only thing notable in here is this first part down through step 20 was a 320 by 192 by 16, and I could use HPrint or anything that the high-res stuff did. When I switched over to 256, 225, didn't have any of that available to me. So I added my letters, and you'll find that in lesson 18. All the letter stuff, you can print anything you want on the screen from at any place. Okay, here's Glen's Sprite demo again. We're talking about that. I needed a coordinates table. And this is derived. You can call it derived, you can call it stole, copied, plagiarized, whatever. I used the same table he had in his program. And all that table was a real long table that had column row in it. Like I said, FCB 13416. Just a long list that I just copied it out and used it. And what I needed was, I wanted to, as opposed to keeping the row column, I wanted this actual screen address. So, and to come up with that address, you got a row times the width of the screen divided by 2 plus the column plus where a screen begins at 2000 to come up with an address. And this 13416 calculates out to hex 2843. So what I first did, I just took, instead of taking this whole table I just wanted to work with, I took maybe 20 or 30 of them I copied out of his program, put the word data in front of them, and wrote a basic program. This was just a bunch of data statements in there. And I'd read these first 2 in. I would calculate it and write out to a file, space, FDB 2843, and go on to the next one. So I had all the ones I took and put down there. So, okay, that works pretty good. And I used them in my program and got all of it working. It was good. And I said, okay, I need to bring forward the whole table. And I knew it was big, but I didn't realize how big. So I went and I copied it out of his program. It turns out there was 2,915 FDBs that would come out of there. needless to say, with the data statements, it would not fit in a basic program. I mean, it just was way too big. So, I mean, it was no big deal. I just had to rewrite, just change the program instead of putting them in the program with data statements. I just read the file in, read this one in, calculate it, print it out, read in, file. Did that 2915, wrote out to a file, and I added one to it. And then I could just, when I went to compile it, okay, I put a coordinate, a tag name on the front and an end statement. And I compiled it. It had 2916, 2915, and the one I added times 2 is 5832 bytes, or hex 16 Charlie 8. Well, if you add that to E00, it comes out to 24C8. Remember, our image starts at 2000, so that wouldn't. And besides that, that's no code. That's just a coordinates table alone, which told me I needed another block that I could bring in and address it from someplace else, which is what I did. And what I did, I got it to work and addressed it at A00. I'll show you how I did that in it's in the basic program. And here's that. At A00, you find that coordinate. At A02, you find that coordinate, and so on and so forth. Okay, I remember now that table's got 2,915 of these entries out there. Okay, it takes up most of a whole block. So what we got here is kind of an overview. What I did, we got an object one, which is one of the baseballs. That object contains 4 separate things. One, the 1 byte control table has things in there. Is this the last one in this sequence? Restore, yes or no? I don't know, stuff like that. And then it has the address in this coordinating table that this ball is working with right now, where I can find what address he's working on. And we have the current address on the screen and the previous address on the screen for restore purposes. And then here we got 3 of these objects. When in real life, you can have up to 12 of them. And just assume now that we're not going to worry about the first time through restoring, because there's nothing to restore. We'll just assume we've been through here before. And we come through the loop to object 1. We get this coordinate. What's the address that you have been working with? It was A0, or we're going to work with A00. We get this address out of there. Well, get this address. Sorry, let me back up. We come in and get the coordinate table that's in there. We add 2 to it, bump down to the next one we're going to put on the screen, and get this address. We store this A002 in the coordinate for next time. We take the current address down here, move to previous, and the current address we put in here. We take the previous address, we restore the screen, and then take the current address and put it in the new location on the screen. Go to the next object, do the same thing. He's here at 4. We bump down, get this, what's at 6, which is this. We save the A006. We move the current to previous, the new address to current, restore, print. Just go through it now. One thing to note on here, we're pretty close. And the first one, if it's here, the second one, I think the closest you can be is like 10 down, so it'd be down 10 entries, so it'd down be 20 bytes. It'd be way down here, because otherwise they'd overlay one another. So you get the first one's here, second one's here, the third one's down another 10 or 20 bytes or so, and so on and so forth, up to 12 of these objects. Okay, which means they're always apart, but they all keep moving apart. And if you get to the end of this table, it starts back up at the beginning. So anyway, that's how it works. And objects, we go ball 1, ball 2, ball 3, in, to go back to the top, and go through it, just keep going through. Common stuff, but for some new beginners may want to see exactly how it works with something like that. Okay, optimization. Okay, here's our Sprite. Okay, 13 rows and 7 bytes for columns, or 14 pixels across. Okay, rows times column, 91 bytes, or 182 pixels in there. Okay. here's the different cycles that I kind of calculated by using in LW tools. You can turn on them cycle counts. And the best I could make out, because it's not hard coded for every pixel, okay? It takes about 7100 plus or minus in just a normal screen, and to restore it 2256. They were both pretty good approximations. Now, if you go into stack blasting, it's 459 bytes, period. There is no if, ands, or buts. That's what it is. You see a lot of difference there. And to restore, and I'm saying stack blast because there I used a push over here, and this here just did stores, and this does the push. How's this come about, all this here rows and columns? Okay, I took that, let me back up. I took this first row out of there, first and second row, and put them on here. Okay, and this is what it looks like in memory. Okay, the background uses palette register number 7, which has white in it. So these are all the background, the whites. 8 has the black, which is down here. If you look at these 3 pixels here, and then white again. On the next one, we got 3 backgrounds, 2 blacks, yes, or 2 blacks, 1 gray, so on and so forth. So that's just there. Now, if you're working with these and you want to, with these 16 color and 2 pixels per byte, you got to work with each pixel at a time. Okay, what that means is, for if you're going to put this on the screen, you can read this byte in, you're getting 2 pixels. And what to do to be as fast as we can, compare that with what's already on the screen. And if you're working with, you're in the background, you compare it, it's got 7.7 in it. You say, okay, I'm done. I don't need to do nothing. I'm done. Get out of here. Go get the next 2. So that'd be very quick. Just a very few cycles, very few instructions. Read in the next byte, it's got 7.7. Again, if you're out in the middle of the background, it's quick. If you're on top of Mickey and it's red, we'll do something different. You get the next byte, it's got 1 pixel's background, 1 pixel is black, right there. So what we have to do is split this apart and work with 1 pixel at a time. So you need to AND that byte and just keep the most significant bits, the 7. And then we got to get to what's ever on the screen currently. Okay, whatever's where we're going. And that could be the red and Mickey, or the yellow, or it could be just the background again. And you have to compare it and determine you got to split it and determine what to do with it. If it's a 7, you want to use what's already on the screen, because that's almost 7 is almost like a transparency byte. If it's like when it's the 8, you know it's going to be new. Okay, regardless what it is, that's new, and you're going to put it on the screen. So you have to OR these 2 pieces of information, the most significant and the least significant bits. You got to OR them back together and store it on the screen. And that's what takes so many cycles, is when you get down here and they're all each pixel at a time. Okay, as you see, and there's no backgrounds in here, so you're working with each one, all 91 bytes, okay, that you got to work with, split everything in back. That's why it takes a lot of cycles. When you look back, that's why it takes about 7,000 to go through doing all them cycles of splitting and then merging or back together. And with stack blasting, it just goes, now here's stack blasting of my interpretation with interrupts turned off. So we'll see what it looks like. This is the whole 2915. You can see it's much quicker than it was. And that's running with 8 balls. If you're running with 4 balls, you can't hardly even see them, because the less you have is the less the instructions. But that's stack blasting for you. You see it's going all over the screen and going pretty quick. And this is the whole 2915. In fact, it's a little bit more than that, to get kind of back to where it started, which is coming up here real soon. There, we're back to where it normally started, and we're going to end up right about there. So that's what stack blasting does for you, as opposed to the other thing. Okay, one thing I want to show you, this is the basic, if you're running the basic program, which is called Sprite 45, and I'm going to provide you with the disk with all the code on it and this basic stuff. First time you say run the program, first time it prints on the screen, first time load programs, yes or no. Or you want to say yes, you want to get all the programs loaded. Then it will tell you to press any for defaults. And then it's going to ask you number of sprites you want or number of balls in between 4 and 12. And here I typed in 8. Sprite separation anywhere from 10 to 16. That's the number. Well, let's just say pixels apart. It's a little bit different in pixels, but that's how far apart. And a loop counter anywhere from 20 to 4,000. I just used 592. My 592 has a hex 250. And stack blaster normal. I put in normal and run it. And that's what you've been seeing a lot of it. It's, runs slow, but it all works. Then when it ends, it comes back here and you can just type in run again and it will say, want to load the programs? You can say no, because they're already in there, and then do defaults. This time here, I said number of sprites. I just hit the enter key, okay, and I got 8, okay. And here I typed in 12, 333, and then stack blast, and then it comes ready, you say execute, and it goes again. If you hit enter on each one of these entries here, here's the defaults. You'll get, okay, 8 balls, separation of 16, 592 cycles, and normal lasting. So that's kind of it. I'll put all those various links for all this different stuff in down below in the area, and you can go from there. So that's it. Like I say, this is more of a demo than it was for a lesson, but hopefully somebody will get something out of it, and that will be all for this one.